mechanics. We are going to take off today by reviewing what we did that last Tuesday briefly, maybe in 5 minutes or 10 minutes. Then we take off with other aspects of mechanics. Yeah, I've told you that the four fundamental concepts used in mechanics are space, time, mass, and force. And we started with we did a lot of I treated forces more explicitly that last Tuesday. We're talking about Newton's law of Newton's law of motion, the 3 laws of motion. We treated them in details. Newton's 3 laws of motion. We treated them in details. So we are still going to talk about them today by way of revision. After that, we can now proceed. Now, I remember I told you that Newton's first law of motion state that if the resultant force acting on a particle is 0, what we mean by the resultant force is that if there are two bodies or a single body, and there are 2 forces acting on it from left and right or from up and down, if the resultant force is going to be 0 if the forces balance out, if they are equal. Yeah, so if the resultant force acting on a particle is 0, then the particle will remain at rest. That means if you don't move, is it clear to you? The particle will remain at rest because the forces acting on the body, that particular body balance out, so they are equal. So if originally at rest, or it will move with constant speed in a straight line if originally in motion. I believe it's clear to everybody. So that is what Newton's first law of motion. But if your physics textbook, the definition is going to be simpler than this. Because we are now in advanced level, I try to make it a bit complex. Now, by resultant force, because I was talking about resultant force. By resultant force, what we mean is that the sum of the individual forces which act on the body. Is it clear? I remember I told you that day that if the forces are acting on the opposite direction, you are going to add them together. They call it resolution of forces. You would have done this in physics. They call it resolution of forces. If the forces are acting in the opposite direction, maybe one is acting north while the other is acting south, then you are going to add the forces together as F1 plus F2. Is it clear to you? Which means if F1 is 10 Newton and F2 is 15 Newton, then the resultant force is going to be 25 Newton. I believe it's clear to everybody. But if the forces are acting in the same direction, the forces acting on the body are in the same direction, then the resolution of those forces is going to be negative. You are going to subtract, which means 15 minus 10, because the F1 is 10, while F2 is 15. So 15 minus 10 is going to give you 5 Newton. So when you resolve the forces that are acting on that particular body, then you are going to have 15 Newton. That is what is called resultant force. I believe everybody understand now. Yes, so we proceed from there and we quickly go to Newton's second law of motion. There are diagrams to illustrate all these things. I will not go through them again because we already have them. Then, because we are dealing with technical mechanics, there is an example there in figure 2.13. You can see an example there. Is it clear to you? So you could use that example of a boat that is on top of a river. When that boat is on top of a river, there is a force that is going to be acting at the base of the boat. This thing is not just a boat. Even though you put a plate, for example, take a plastic plate, put it on top of water. Just experiment it today after the class. Take a plastic plate, fill a bowl of water. If you have a swimming pool, just say a bowl, fill a bowl to the top or even to the middle and drop a plastic plate on top of it. You will see that the plastic plate is not going to sink. It's going to remain on top of that water. Why is it like that? Because the upthrust, what is also called the force of buoyancy, that is acting upwards from the water, and the weight of the plastic plate or whatever, whether it's a container, whether it's a spoon or whatever you drop on top of the water, they balance out. Is it clear to you? So when you resolve the force, you say that you're going to add them. So that is that. So for this reason, I was trying to use it to also explain to you the Archimedes principle. Where the principle, this is the principle they use to create ship, all those ocean liners, ocean going vessels. This is the same principle they use to create them. Is it clear to you? So we end it there. We go to Newton's second law of motion. Now, Newton's second law of motion, it says that if there is, I'm going to define it in a normally, but I'm still going to use this advanced level material to define it. But let me define it with the advanced level material first. It said that if the resultant force acting on a particle is not zero, you get it now. You know, from Newton's first law of motion, we are dealing with a resultant force of zero. Here in the Newton's second law of motion now, we are dealing with a body where the resultant force is not zero, which means the two forces that are acting on the body, they don't balance out. Which means a force is acting that is greater than the force that is acting downwards and the force that is acting upwards, they are not equal. That is why the resultant force is not going to be zero. So if we have a situation like that, according to Isaac Newton, he said that if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant force and in the direction of this resultant force. I believe it's very clear. I come again. If the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant force and in the direction of the resultant force. I believe it's clear. So now, there is an illustration for it, but since I gave you that last time, I may not need to explain it again. But you already know the unit of acceleration, you know the unit of force, you know the unit of mass, the unit of time. All these things are known. The unit of length, distance, all these things are known. Now, the unit of mass is kilogram in SI unit. The unit of force is Newton. And the unit of acceleration is meter per second square. So those forces are already known. Now, if we are to practicalize it, it is as if the water were removed from beneath the boat. In that example I gave to you just now, which means that plastic plate I asked you to drop on top of a pond or a river, it's assumed that you now remove the water, you throw the water away from the container, and you now drop the plastic plate just at the base of the container. That is what Newton's second law of motion is explaining. A non-zero resultant force would act, and the boat would accelerate downward. Is it clear to you? So for this reason, materials also sink. Is it clear? It's for this reason that materials sink. When you hear that, I was making example that last Tuesday. I said when you throw a stone inside water, you don't need to be told that the stone is going to sink instantly. It's going to sink. Is it clear? So that is that. Now we go to Newton's third law of motion, because this is not our main focus for today. I'm just revising. We go to Newton's third law of motion. The Newton's third law of motion states that there is O-level definition. Said in every action, there is always an equal and opposite reaction. I come again. For those that were not in the class that last Tuesday, this is an opportunity for you to understand what we did. It said that in every action, there is Newton's third law of motion. It said that in every action, there is always an equal and opposite reaction. That is the basis of Newton's third law of motion. Now, in this material, it said each force of action has an equal and opposite force of reaction. Are you following? So what this means is that the force applied, the force that you apply, maybe you are moving, when you are moving a particle or a material, is the same force with which you come back. Is it clear? So similarly, in real life, these things are reoccurring in everyday life. For example, in your car, all the components, all the components of a car, for example, are based on these principles. Other machines, all the machines you see, they are based on this principle of Newton's law of motion. Most of them, you see all these things in action, like this third law of motion in action. For example, when you have a turn effect, for example, when you have a pulsating force, for example, in a grinding engine, where you have a force that is going up and down, the force with which it goes up is the same force with which it comes down. Is it clear? That is actually on the Newton's law of motion. Is it clear? Third law of motion. That is the rate at which a body goes up is the same at which it comes down. So that is that about Newton's law of motion. I believe we ended it here that last time. Now I am seeing here, we are going to talk about scalar and vector quantities as we progress. We are going to talk about scalar and vector quantities. Now, a scalar quantity is a physical quantity that has only magnitude. Please write down. We are talking about scalar and vector quantities here. Scalar and vector quantities. A scalar quantity is a physical quantity that has only magnitude. Is it clear to you? Why a vector quantity is a physical quantity that has both magnitude and direction. I don't know if it is clear. If it's not clear, we have to come again. A scalar quantity has only magnitude. It's a physical quantity that has only magnitude. While a vector quantity has both magnitude and direction. Examples of scalar quantities are mass. Is it clear? They call it MKS. You would have done these things in your physics in SS1. SKS. They would have taught you what is called SKS in your O-level physics. That is meter, kilogram, and second. The basis of scalar quantities is what is referred to as MKS. That is meter, kilogram, and second. Those are scalar units. So, but the quantities are length or distance, mass, and time. I believe it's clear to you. So when we say MKS, in reference to scalar quantities, then we are talking about distance, what you can also call length. We are talking about mass. We are also talking about time. Now we know the meaning of length. Length is the distance between 2 points. The distance between 2 points, that is length, is distance between 2 points from one point to the other. Now we can measure the distance between Lagos and Abeokuta. We can measure the distance between even within Lagos. We can measure the distance between Egbeda and VI. We can measure the distance between Ikoyi and Lekki Phase 1. That is what we mean by length. And I told that the unit of length is in SI unit is the meters. Then we have what is called the mass. Mass is the quantity of matter in a substance. I suppose I defined that last time. Mass is the quantity of matter in a substance. Is it clear to you? So that is that. And the unit of mass is kilogram. Now, when we are talking about time, we know that time is infinite. It's very, very complex. When we are talking about time, that is what it takes, the duration for that an action takes. That is the layman definition of time. The duration of any event. Is it clear to you? And time is measured in seconds. Now, time is in physics and in mechanics, time is one of the most valuable quantity that we cannot do without. So, vector quantities, that is quantities which has both magnitude and direction, associated with them are represented by bold letter like F. Is it clear to you? Okay, I didn't give example of vector quantities. I was saying that vector quantity, they have both magnitude and direction. Example of vector magnitude, you have things like force. Is it clear to you? Things like force of gravity, any type of force is a vector quantity. You have things like acceleration, things like velocity, etc. are examples of vector quantities. In the last class, I was trying to define force for you. I define force. I didn't define it theoretically. I only define force mathematically, where I said force is mass times acceleration. Now, in your physics textbook, if you go to your physics textbooks, there's nothing you will see there when they are talking about force, other than they will tell you force is push and pull. Is it clear? That is the simple definition in physics textbooks. They define force as push and pull. Most times you get to some shopping malls, you will see the door, they will tell you to push. Some they will tell you to pull. So in a layman language, that is simply force, where you have to push it to enter, or you pull it to yourself to enter. So in basically, force is defined as push and pull, but it's more than that. But for easy understanding, that is force. Now the symbol for force is capital letter F. Scalar are represented by italics like M. That is small letter M. The magnitude and direction of vectors are illustrated in figure 2.12. You see there, you see figure 2.12 there at the beginning of this material. You will be seeing at the top where we're talking about polygons. And you will be seeing there in figure 2.1. You are seeing F1, F2. Is it clear? Those are vectors, and F3. Those are forces that are acting on a particular body from different directions. And you not see them there. You see, and it's represented by a straight line with an arrow. A vector is represented by a straight line with an arrow. that is anywhere you see vector, either the vector is going upward, that is north direction, or going downward in the south direction, it must be represented by a straight line with an arrow sign. That shows that it's a vector. These vectors can be going in the same direction, where you have two straight lines with two arrows going in the same direction, or they can be going in the opposite direction. Is it clear to you? But whether they are going in the same direction or opposite direction, you have it to be F1, capital letter F, and F2 for both upward and downward action of these vectors. Is it clear to you? Yeah. So that is that. I've tried to. If you go to page 2, you are going to see example of these vectors there. So that is that. So I continue with the explanation for vectors and scalars. Yeah. Now, if we set F to be 0 in Newton's second law, for example, you are going to have the body is going to be is going to sink, as I explained to you. It's going to sink. But in the first Newton's Newton's first law of motion, you see that because the forces balance out, the body will be, the forces acted from downward force and the upward force, they balance out. The body is going to remain as it is. So that is that about vectors. But there are other things that we need to talk about, but we are not going to, because this is not our main topic for today. We will not spend too much time on it. So I think that is that about it. Let me see whether I can add something to it here. This material, we have exhausted this first material. In our next class, we are going to come with another material. Yes, so let me quickly add that Newton's laws are used in the analysis of the most basic problems and in the analysis of the most advanced complex problems. Is it clear to you? So now when you get to, for example, you get to a port, like a paper port now, you see crane everywhere, or you go to a building site, you see crane moving heavy load up and down, maybe from the ground floor to the 25th floor. Just know that, appreciate that those are Newton's laws of motion are in operation there. Is it clear to you? Or when you get to any building site, or you get to where they are building a bridge, know that Newton's law of motion are going to be there. Most of the equipment that are used in construction, mechanical, civil, production, all of them, they are based on this Newton's law of motion. So what we are saying in essence is that Isaac Newton revolutionized the mechanics, this topic called mechanics, and make a life more easy for people. So that is that. You see that in everyday life, in your homes, in your offices, construction sites, everywhere. So that is that about Newton's laws of motion. Now, we are still going to continue with Newton, but today we are going to be talking about Newton's law of universal gravity. Please write it down as a topic. Newton's law of universal gravity. We are going to talk about Newton's law of universal gravity. Then we are going to talk about, from there we are going to be talking about contact forces and elastic forces. We are going to talk about them briefly. When we come back next week, we are going to talk about them in detail. So for today, the main topic for today is Newton's law of universal gravity. So you have to write it down as the course progresses. Now, definition. Newton's law of universal gravity, O-level definition now states that any two bodies of matter, please write down Newton's law of universal gravity. You can go to your physics textbook, you see it there. State that any two bodies of matter, that is, the bodies are going to be two. Is it clear to you? That is M1, M2, two bodies that are not together. Is it clear to you? M1, M2. That is two bodies with different masses. Is it clear to you? So any two bodies of matter attract each other with a force. Please write down. Any two bodies of matter attract each other with a force which is directly proportional to the product of their masses. I believe people are still writing. Any two bodies of matter attract each other with a force. Any two bodies of matter attract each other with a force which is directly proportional to the product of their masses, and inversely proportional to the square of their distance apart. If it is not straightforward, I'm going to define it for you again, and I'm going to explain it, and I'm going to also use the material I have here to explain it for you to understand it, for better understanding. So now I come again with definition of Newton's law of universal gravity. These are all part of mechanism. Yeah. So I come again. I said any two body of matter, that is two different masses, two bodies. Like what we mean by two body of matter, we can a building and a ship at sea. See a lighthouse, for example, a lighthouse or two ships at sea or three ships at sea, or let your demonstrate to two ships at sea. That will be a two body, or two men that are close to each other. Maybe somebody is standing 50 meters away from another person, or two cars that are parked. Two cars that are parked in a compound. One is at the edge, one end of the compound, one is at the other end of the compound. Or two houses that are close to each other. That will mean by two body. So when I say any two body of matter, know that we are talking about hard surfaces. These things are every day, they happen around you, but you don't know. So any two body of matter attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. Is it not clear enough? So that is Newton's law of universal gravity. No, now mathematically, if we are to state Newton's law of universal gravity, don't forget that there is a proportionality sign there. For those of you that are good in mathematics, you will know that I said any two body of matter, that is Newton's law of universal gravity, state that any two body of matter attract each other with a force which is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. That will tell you that there's a proportionality sign there. If there's a proportionality sign, when the sign of proportionality is removed, then a constant must be introduced. You know all these things in mathematics. The removal of the constant of the proportionality sign we introduce. With the removal of the proportionality sign, we introduce a constant. That is the rule in mathematics. So when I remove the proportionality sign now, a constant is going to be introduced. That constant is called big G. Are you following? The constant that will be introduced is known as big G. That is capital letter G. So when you now remove, first of all, come like this by saying F is proportional. No equality sign there for now. Say F is proportional to M1, M2 over arrow square. That arrow is distance apart. Some people can use D square, distance apart, or S square, distance apart. It's the same thing that you want to use. Now, when that proportionality is now removed, we are going to have it to be Newton's law of universal gravity it will now become F equals G. That is big G. Please take note, there's a difference between big G and small g. This big G is capital letter G. Don't forget that we also have small g. Small g is different from this G we are talking about now. Small g we know is acceleration due to gravity. Is it? This one is not acceleration due to gravity. This big G is not acceleration due to gravity because we are not talking about bodies that are falling from the sky. But if two bodies are also falling from the sky, this law also apply. But in that case, big G and small g will apply. But now we are talking of two bodies that are at sea, two ships that are at sea, or two bodies that are on land. Is it clear to you? That's what we are talking about. So F, capital letter F, equals G. Please don't use small letter G here for Newton's law of universal gravity. What you are going to use is big letter G. So you say F equals G, M1, M2, or you can say M1 times M2, anyone you want to do. We already know in mathematics that M1, M2 is M1 times M2. So you can decide to put the sign, you can decide not to put, you can decide to put a dot in between M1 and M2. It shows that you are multiplying over arrow square. That is mathematical representation of Newton's law of universal gravity. And I believe this is understood to everybody. So I'm going to continue. Now, every pair of particles affect each other. I believe it's clear. It's what I've just been explaining. I'm just still explaining it in another format. Every pair of particles affect each other with gravitational forces. Now, some people that don't understand this topic will be saying, how can we be talking of gravity when these bodies are not suspended in air? For example, two ships that are at sea, or two objects that are two vehicles that are parked in a compound. How do they attract each other? Please take note that whether it's not always material that are suspended, that are falling objects that are subject to gravity. Even material that are at rest, if a body is at rest under gravity. Please take note of that and know it from today, in case you didn't know before. Gravity does not only act on falling objects. Objects at rest are also subject to gravity. So these objects these two particles that are far apart or that are close together are attracted by forces of gravity. Please take note of gravitational forces. The gravitational forces or force is a central force of attraction. Please, you can be writing. Let me come again so you can be writing. I said every pair of particles affect each other with gravitational forces. Full stop. The gravitational forces is a central force of attraction. Full stop. That is, a pair of particles are drawn towards each other. Just like the way a magnet is going to attract a magnetic object or substance when the substance is active within the region or what is called the field, magnetic field. When a magnetic object is close to inside a magnetic field, a magnet will always attract it. It is only when that object is very far from a magnetic field, that is when a magnet cannot attract a magnetic object. That is a similar scenario we are painting here. That hardwares, see, if you keep two laptops in your room, those two laptops are attracting each other. Whether they are close to each other or they are far from each other. But the farther, the lesser the force of gravity. Is it clear? From that law of universal gravity, where we're talking about inverse proportional to the distance apart. So that is that. So that is, a pair of particles are drawn towards each other, and the gravitational force acts along a straight line connecting these particles. Please, I'm going to come again because this technical mechanism, everything is supposed to be technical, not theoretical. So that's why I'm taking time to give practical examples. So I come again. I said that is, a pair of particles are drawn to each other, towards each other, and the gravitational force acts along a straight line connecting these particles. So there's a line that is connecting two objects. So example of forces of Newton's law of universal gravity, a practical example are two ships that are at sea. Whether they are far from each other, whether they are close to each other, Newton's law of universal gravity acts on them. They are attracted to each other. Whether they are 100 miles away, whether they are 100 meters apart, whether they are 200 meters apart, there's a force of gravity that is Newton's law of universal gravity acts on them, drawing them together, attracting them to each other. That is the basis of Newton's law of universal gravity. Now, I give an example. Although we are not solving. It's just also a practical example. I said gravitational forces between two particles with masses mp and mq, respectively. I come again. Assume that gravitational forces between two particles with masses, let me say, assume there are gravitational forces between two particles with masses mp and mq. That is, you remember I used m1 and m2 before. Here I'm using mp and mq. It's the same thing. With me, we are dealing with two masses. That is, the mp is a subscript at the down of the m, and take note that the m are capital letters. Or one of them can be capital letter while the other one is small letter. You can decide to do it like that. In some books, they do it like that. The M1 is, or some books, what they do, instead of saying M1, M2, they will just say capital M and small letter m, so that they are dealing with two masses. Anyhow you want to do it, there are no hard and fast rules as to how you are going to represent the masses that are going to be attracted to each other by Newton's law of universal gravity. So that will take us to the example, a practical example I'll give it to you. There are the two particles acted on by gravitational forces with masses mp and mq respectively. There is an attractive force with magnitude. What's going to be the attractive force between the two particles? I come again. Two particles are acted on by gravitational forces. Okay, let me come again by saying the two particles have masses mp and mq, and they are acted on by gravitational forces respectively. There is going to be an attractive force between the two particles, mp and mq. The attractive force between the two particles is F equals G equals G mp times mq over r squared. I believe I have not confused you. So I'm going to come again. It's the same law I gave to you before, where I said F equals G big G M1 M2 over R squared. Is the same thing here. But here, instead of M1, M2, I'm using MP and MQ to represent the masses. That is the two particles that are acted on by the force of gravity, or Newton's law of universal gravity, or Newton's law of gravitation. The force I go to divide the magnitude means size. Size of those two particles is F equals G over R squared. Now, the value of big G is 6.67. That is your 6.67 times 10. 6.67 times 10 to the power minus 11 kilogram per m square. Is it clear to you? That is the symbol for this G. The value of G, the value of big G is 6.67 times 10 to the power minus 11. That is the value for big G. So please take it like that. Now we are going to, while I'm still on this Newton's law of universal gravity, G is gravitational constant. R is the distance apart between the two particles. Is it clear to you? R can be in kilometer, can be in meter, can be in whatever unit you want to put it, but it's basically in meter and kilometer. Is it clear to you? So that is that about Newton's law of universal gravity. So we are through with that topic. What I'm going to do for you when we come back next week is that I'm going to give maybe a practical calculations based on it, or maybe today before we close, I'll be able to give you practical examples on it. Yeah, so now we'll now quickly go to what is called contact forces. Is it clear to you? We are going to do what is called contact forces. Now, this force we are talking about in Newton's law of universal gravity is not a contact force, in that the two ships that are at sea are not touching each other. Is it clear to you? They are what you can call induced forces. What you can call them is induced forces. The forces are induced, they are not in contact with each other. So, but now we have dealt with induced forces. Now, what we're going to be dealing with here now, which I'm going to introduce, which we are going to build on as from next week, is contact forces. Now, what are contact forces? Contact forces are forces where the two bodies are touching each other, they are in contact with each other. Is it clear to you? Forces that are in contact with each other are what are referred to as contact forces. Now, we hear of frictional. Example of contact force is frictional force. Frictional force. Is it clear to you? Frictional force is a typical example of a contact force, which implies that the two bodies are in contact with each other. For example, when you are putting on shoes, for example, you are able to move up and down, or even if you are not putting on shoes, you are moving with your bare foot, you are able to move up and down without falling because there is a contact force between the sole of your feet and the hard surface. Either you are moving, I'm moving on tiles now in my living room. Now I'm still walking. I've not fallen down. But if, for example, this oil was spilled all over this place, we should spill oil all over tiles, for example, or you pour water all over tiles, for example, you see that no matter how careful you try to move, you are going to slip and fall, because the force of gravity, the frictional force reduces. Is it clear to you? The frictional force reduces. Now, the benefit of frictional force in nature cannot be overemphasized. The benefit that we derive from frictional forces in everyday life, you are sitting on a chair comfortably, we call frictional force. You are able to move from one place to the other, we call frictional force. You are able to drive your car from one point to the other because of frictional force. You are able to, even trains, they are able to move on train tracks because of frictional force. Is it clear to you? So those are examples of contact forces. Now, when we are dealing with contact forces, we have what is called solid contact forces, where the one I'll be explaining to you. For example, when you are hitting a nail, when you are nailing wood, and you are joining two wood together, for those who are in carpentry workshop, without frictional force, you cannot put a nail on wood or on the wall or anywhere. Is it clear? So because of frictional forces, we're able to do that. I'll give you examples of these things. Even plane that is flying from one part of the country to the other, or even outside the country, they're able to do it because there is frictional force between them. But that type of frictional force is different from the solid frictional force I was telling you about. Now, friction in solid is called friction. Is it clear to you? Frictional forces in solids, like I'm sitting on a chair now, my laptop is resting on the table, my book is resting on the table, my biro is resting on the table because of frictional forces. Is it clear? That is solid frictional force. Now, there is frictional force in fluid. Is it clear to you? Water, oil, engine oil, different type of fluids, they all experience frictional forces. Is it clear to you? You understand what I'm trying to explain? So, for example, if you bring water, you bring engine oil, you bring red oil, you bring different types of fluids, and you try to put a nail, or you try to put a hard object, a coin, inside these different materials. The time with which the material will get to the bottom of the jar or the container, it is going to be different. You know this. You can experiment it later. Pour water in a container, pour engine oil in a container, pour diesel in a container, pour red oil in a container, and put a coin in each of them at the same time. You see that the time with which they will get to the bottom of the container is going to be different. Why is it like this? Because of resistance. That is frictional force. Because frictional force is acting on the coin. Is it clear to you? So that is an example of frictional. Now, all these things, as I told you, they find application in everyday life. For example, in boilers, what we use in power generation, boilers are very important part of everyday of production, industrial production. In boilers, in refining, in different industries, even in the automobiles, all these things find use. These contact forces, they find use. So that is that about contact forces. I've defined friction. I've told you about frictional forces in solids. I've told you about frictional forces in liquids and gases, which are together referred to as fluids. Gases and liquids together are called fluid. Please write it down. Gases and liquids are together referred to as fluid. So there is frictional forces in fluid, and there is frictional forces in solids. And these frictional forces find application in everyday life. They find uses in industrial production, in transportation, in aviation, in every sector of life. These things find usefulness. Is it clear to you? So you already know, you will appreciate the fact that without frictional force, you cannot move from one point of your house to the other. You cannot even trek. You cannot even walk outside your house. You cannot drive. You cannot do virtually nothing you can do without the forces of friction. That is what is called contact forces. So this is part of mechanics. Now, from there, we will quickly push to what is called elastic forces. Please take note that all these things I'm telling you now, we are still going to come back to them in a better form when we meet next time. So now we are going to be talking about elastic forces. Elastic forces. Yeah. In talking about elastic forces, we know that there are some materials that are elastic. What we mean by material is elastic is that when you stretch this material, when you are, let me use stretch. Because we are in a physics class, let me say when you apply a force to this material, you know that naturally it's going to stretch. The material is able to get back to the original position. Is it clear to you? That is what is called elasticity. Elasticity is the ability of a material to return to its normal position after distortion. Please write it down. Elasticity. Elasticity is the ability of a material, engineering material for that matter. Engineering material, you can use engineering material, you call materials engineering material anyway, to return to its original position. After distortion. Is it clear to you? So that is what is called elasticity. Now, the scientists that revolutionized this topic of elasticity is called Hooke. Now, I'm going to quickly explain to you, define for you Hooke's law, and from there, I explain the everyday application of elasticity and elastic forces, and we close. Now, Hooke's law states that if a body or a spring, let me use spring because we are dealing with elasticity here. Now, let me explain to you in an everyday language that you are going to understand easily. Now, say if a spring is fixed at one point, if a spring, you know what we call a spring, anything spring, whether it is this scale, this hand scale they use in buying cocoa, or any spring that you have. If you go to wristwatches, you have weak springs inside. You have spring everywhere. If you go to shock absorbers of vehicles, all those heavy, they call it articulated vehicles. You see all those what they call shock absorber there. Those are springs. When you go to all these small vehicles too, you see shock absorbers. Those are springs. But the spring of an articulated vehicle like a trailer, those Dangote trailers you see everywhere, and the spring of a regular vehicle are not the same. They're not going to be the same because they are not carrying the same weight. Is it clear to you? So that will make you to understand because we are dealing with technical mechanisms. So now Hooke's law, he said if a spring is fixed at one end and a weight is attached to that spring or a load is attached to that spring, the extension of that spring will be directly proportional to the weight that is applied. I don't know whether you people understand what I've just explained. I don't know whether you understand what I've explained by Hooke's law. Now, Hooke's law states that if a spring, I use a spring because it's elastic, is attached at one point and a weight is applied to that spring, the extension of that spring will be directly proportional to the weight attached if the elastic limit is not exceeded. Is it clear to you? So long as the elastic limit is not exceeded, you can even start the definition by using elastic limit. Okay, so I come again defining Hooke's law my own way. Hooke's law said that if the elastic limit is, so long as if the elastic limit of a material is not exceeded, of a spring or any material is not exceeded, then the extension of that spring will be directly proportional to the weight attached to the other end of that spring. So now just look, for example, look at it now. For example, you have in a workshop, mechanical workshop, you know the way they do mechanical workshops. Now you put a hand scale there. And put a weight, maybe one half bag of cocoa or 10 blocks or 7 bags of cement, you attach them to the end of that scale. You see that if you put 2 bags of cement, for example, the scale, the spring is going to extend. If you put 5 bags, it's going to extend. If you put 10 bags, it's going to extend. If you put 15 bags, it's going to extend. But the extension when you put 2 bags, and when you put 5 bags, and when you put 10 bags, and when you put 15 bags, are never going to be the same. I believe you appreciate this. Is it clear? So they are not going to be the same because the weight are different. But Hooke's law continue to the scale or the spring or the material will continue to obey Hooke's law forever, so long as the elastic limit is not exceeded. Once the elastic limit is exceeded, then Hooke's law is no longer obeyed. Is it clear to you? So that is that. So in Hooke's law, we have what is called the strain and the stress. I think you are going to explain those one to me in assignment. Strain, stress, and Young modulus. All those things you are going to explain that to me. Young modulus. Those are things you are going to explain to me. What we mean by stress, that is extension over length over extension, F over A, etc. You are going to explain them. So that is that. Now, Hooke's law find application in every aspect of life. For example, in bridge construction, in house construction, in construction of ship building, all these MTN masts, all this mast construction, all sort of construction you see in life. See, Hooke's law is applicable. Now we hear issues of building collapse all over Lagos. You hear that this building has collapsed, this other building has collapsed, the material has given way. Is it clear to you? It's because they did not take cognizance of this Hooke's law. Is it clear? When you put a weight that will make a material to extend indefinitely, to exceed the elastic limit, that there is going to be a collapse. So I believe you now appreciate why buildings collapse. When you have to say the building has collapsed in Lagos Island, 3 people, workers are trapped inside. A high rise has collapsed in Port Harcourt. Some people are dead. The contractor has run away. Is it clear to you? It's because of lack of application of the theory of mechanism that is leading to all those things. If they apply the laws of Hooke's, they apply Hooke's law. Is it clear to you? You will see that there won't be any deformation, there won't be any permanent deformation, and the material will be able to support the weight that is above it. Is it clear to you? The material that is not going to be able to support the weight that is above it. Now, Hooke's law also does not just apply to in material generally. For example, in steel, you see that most of the building collapse are due to steel material that are substandard. So when they now put heavy concrete is also an engineering material. When you now put heavy concrete on top of steel, because the weight of this concrete is far more than the steel, or maybe the steel was fake steel, then you see that the steel is going to give way and there's going to be a collapse. So that is that. So you are going to quickly take your assignment because we have just I think like 3 minutes to go. So you are going to take your assignment and we'll continue from there after your assignment. So now your assignment for today, I'm going to give you the first assignment. The first assignment you are going to define with equation number 1 as for today. Today is 21st of May 2020. Number 1, technical mechanism. Define Newton's law of universal gravity. Define Newton's law of universal gravity. Define Newton's law of universal gravity with equations. That is number 1. Number 2, differentiate between scalar and vector quantities with examples. I believe the assignment is well understood. So I said, for those of you that did not hear me, are not hearing me very well, because most people used to call me after, or they call the admin, or they call the coordinator that they didn't get the assignment well. So please listen again. Assignment number 1 for today's class. I said define Newton's law of universal gravity with equations. Give me the equation of Newton's law of universal gravity. Is it clear to you? With all the units, showing all the units. Then number 2 assignment, I said differentiate between scalar and vector quantities with examples. So when you define scalar quantities, you give me examples of scalar quantities. When you define vector quantities, you give me example of vector quantities. That's what I mean by that, the assignment I've just given to you now. So for when we meet again, we are going to be talking more about, I'm going to throw more light on contact forces and elastic forces that we started today. We are going to start by revising these contact and elastic forces first before we go to our topic for next, when we meet on Tuesday by the grace of God. I'm going to summarize everything, contact and elastic forces. If possible, I may start from Newton's law of universal gravity before we now take our topic for that day on Tuesday by the grace of God. So stay safe. Thank you very much for listening. Make sure you do your assignment and send to the email. The email is ofsn2002@yahoo.com. Thank you very much for listening. I come again with the email ofsn2002@yahoo.com. Thank you very much and God bless. Lab passing too. Are you finished? It's 2:00. I'm supposed to start my next class immediately. Electrical. Again. Dad, what is the time that they have another class? Go. Every time that they have 2 class. That's what your mommy. Hello, your man. Are you done with the class? Yeah, the first class. I'm through with the first class. Yes, the next one is electrical machine. Yes. I'm getting lost in now. Okay. Don't continue without your material. Okay. Because I don't have. I just left. We were having a meeting before. Okay. So I just left the house. No problem. Okay. Hey, me ask for the time.